Okay, Algebra 2, Section 11.2 takes some of those concepts we took from earlier in 11.1, and we're now moving into the concept of probability, which is what this chapter is really all about. So a definition for us right here, probability is the likelihood of an event occurring. So if you were to look outside and say, wow, it's really cloudy out there, it got dark all of a sudden, and the wind is picking up, you'd probably say there's a pretty good probability that it's about to rain. So probability is just a way that we attempt to numerically quantify how likely it is that something is going to happen. And what we have right here is kind of both a definition but also a formula for how you can find probability. The simple formula for it is that it's a fraction, it's a ratio. It's the number of successful outcomes that could occur, however it is that you define success for that particular experiment, divided by the total number of possible outcomes that could occur. And I don't like that pound sign that I used very well there. So the total number, there you go, of possible outcomes that could occur. And if you follow that formula there, guys, most of your probability problems are going to work out pretty well for you. Now, one little note to write here, because of the way we've defined this right here, your probability is always going to be a number that is in between 0 and 1. The smallest the probability can ever be is 0, and when that happens, that's what we call an impossible event. That's what a probability of 0 means. And the greatest number that your probability could ever be would be 1. And if that happens, if your probability is 1, we say that that event is guaranteed. But most probabilities are going to be somewhere in between 0 and 1. And you guys are going to have the option here, any of them really are fine, of expressing your probability either as a decimal, again, between 0 and 1, as a percentage, now that would be between 0% and 100%, or as a fraction. Any of those three are fine, and in any case, guys, if I was looking for a percent, but you decided to give me a decimal or a fraction, I'm going to give you full credit for that. So don't feel it has to be one or the other, but you'll see moving on here sometimes the types of problem you're working on lend themselves to one better than the other. So let's do some real simple probability stuff here, guys. You're going to roll a standard six-sided die. Now, when most people see this picture over here, they think of the word dice, but I'm going to remind everybody the word dice is actually plural. One of them all by itself is called a die, which is a little bit weird, but okay, that's what that means. And we're going to find each probability. So 4 questions for you here, guys. They'll go pretty quickly. First, the probability of rolling a 3. So the formula we wrote down for probability is the number of successful outcomes divided by the total number of possible outcomes. So we're defining success right now as rolling a 3. So out of the 6 sides on a die, how many of them have a 3 on them? Actually, the one that I'm showing right there, only one of those 6 sides has a 3 on it. Out of a grand total of how many possible things that could happen? 6 possible outcomes. So your probability of rolling a 3, everybody, is 1 out of 6. Now, 1 out of 6 is a repeating decimal. If you wanted, you could write it as 0.16 repeating, or if you wanted, you could write that as 16.6 repeating percent, but I think we can agree repeating decimals are kind of ugly, so fractions are probably the way to go here. Second example, what's your probability of rolling an odd number? Okay, successes divided by total. How many of those sides there out of the 6 are odd? Actually, again, this is weird. It's the 3 that we see. 1's an odd number, 3's an odd number, 5's an odd number. 3 of them are odd out of a grand total of 6. And of course, you guys don't need to be told this. Anytime your fraction can be simplified, you're going to do that. You've got a 1/2 probability, everybody, of rolling an odd number. Okay, on to a couple of weird questions. Number 3, what's the probability of rolling a 9 with 1 die? Number of successes divided by the total number of possible outcomes. So out of all the things that could happen there, how many of those are a 9? None of them, because there isn't a 9 on a standard 6-sided die. Out of a grand total of 6 possible outcomes, and 0 divided by any number other than 0 is 0. And what did we say a moment ago? When you have a probability of 0, that means that your event is impossible. Guys, there's no way to roll a 9 with 1 die if it's numbered 1 through 6. So that's just to kind of verify that notion. How about number 4? What's your probability of rolling a number less than 7? Well, what are the possible outcomes that are less than 7? 1, 2, 3, 4, 5, and 6. 6 of them are less than 7 out of a grand total of how many possible outcomes? 6. And any number divided by itself, other than 0, is 1. And let's go back again. A probability of 1 means that our event is guaranteed. So I gave you these last 2 problems right here just to make you think a little bit. When you have something that's impossible, you get a probability of 0. When you have something that's definitely going to happen, that's guaranteed, you get a probability of 1. But all of your other probabilities, things that might happen but also might not happen, those are going to give you probabilities that are in between the numbers 0 and 1. So let's keep that in mind. Now, the plot thickens, everybody, when now you're going to start rolling 2 standard, and there's the word dice. So let's talk about the probability of getting each one of these possible outcomes right here. And to do this, guys, I will tell you that rolling 2 dice is significantly more complex than rolling just 1. So what we're going to do here, guys, is utilize the idea of something called a sample space to help us work through this. This is what a 2 dice sample space is going to look like here, everybody. Can I... Let me see. I probably want to make that a little bit bigger. Okay, otherwise that might be tough to deal with right there. Okay, here's what's going on here, guys. So maybe I can't move that. Never mind. It's good where it is. Okay, on this dice, this sample space, here's what we're going to do. We're going to talk about the first die up here on the top, and then the second die is going to be over here on the left. Now, when you toss that first die, you've got 6 possibilities. We're going to not use this box right here, guys. Your first die could give you a 1 or a 2 or a 3 or a 4 or a 5 or a 6. The second die, same possibilities. You could roll a 1, 2, 3, 4, 5, or 6. And now what we're going to do, everybody, actually, these lines should probably have been a little darker than all of the other lines right there. Now, we're going to talk about what the actual outcomes are. If I were to roll a 1 on my first die and a 1 on the second die, you would add those numbers up, and the result we just got was a 2. If I rolled a 2 and a 1, that's a 3. 3 and a 1 is a 4. Hey, and I think I see a pattern here. 5, 6, and 7. Now, this looks like it could be tedious, but you'll pick some things up pretty quickly, and it'll start to go faster. A 1 and a 2 is a 3. 2 and a 2 is a... Oh, okay. So all these numbers are just 1 bigger than the numbers above them. All right. 1 plus 3 is 4. This is now 5, 6, 7, 8, and 9. Gotcha. A 1 and a 4 makes a 5. So 6, 7, 8, 9, 10. 1 and 5 is a 6. Okay. And I think we see what's going on right here, guys. And then let's see. We've got 7, 8, 9, 10, 11. And the only time 12 shows up there comes from rolling a 6 and another 6. And that's the only way to get a 12. So let's look at all of those numbers that are in blue right there, everybody. Now, what we're dealing with here is a 6 by 6 grid, which means that we have 36 possible outcomes right here. And the first question I was going to ask you guys now is, what's the probability of rolling a 2 for the sum of your 2 dice? So you'd look at all 36 of these blue numbers and ask yourself, how many of them are 2? And the answer is just 1. Right there. There's only 1 2 that showed up out of the 36 possible outcomes. So your probability of rolling a 2 is a 1 in 36. Now something interesting starts to happen. What's the probability of rolling a 3? There's a 3 there and a 3 here. There's 2 of them. So that probability is 2 out of 36. Now we would simplify that to a 1 over 18, but I want you guys to see these original probabilities out of 36. How about the 4? There, there, there. There's 3. Wrong way. Shoot. 3 of them out of 36. That becomes a 1/12. Now, are we seeing a pattern? Probably. How many 5s do we have? 1, 2, 3, 4 of them. Gotcha. So that's a 4 out of 36, which becomes a 1/9. Okay, how many 6s do we see? 1, 2, 3, 4, 5 of them. So this pattern seems to be holding true here. 5 out of 36. You can't simplify that one. So if I see the pattern here, I'm thinking that 7 is probably going to be 6 occurrences. And there you go, guys. 7, 7, 7, 7. Yep, there you go. There are 6 of those. So the probability of a 7 is a 6 in 36, which simplifies now to a 1/6. But now something interesting starts to happen right here. You might look at this pattern and think that the probability of rolling an 8 is going to be 7 out of 36. But now if I start, oh, that's going to be a pain. Now as I start looking for 8s, now I see, let's see, 1, 2, 3, 4, 5. I got through the major diagonal of this table, and now I'm over here into this smaller corner. My probabilities are going to start going back down now. So the probability of 8 is nope, not that. Probability of rolling an 8 is a 5 out of 36, just like the probability of rolling a 6 was. And the probability of rolling a 9 should be the same as the probability of rolling a 5, 4 out of 36, which becomes 1/9. And I think you guys see what's going on here. The probability of rolling the 10 is the same as the probability of getting a 4 right there, which is going to be 3 out of 36, or 1/12. The 11 is going to be a 2 out of 36, which is 1/18. And the probability of rolling a 12, there's only one of them in that entire table right there, so that is going to be 1 out of 36. So that's what the probability looks like, everybody, when you roll 2 dice. It's quite a bit more complicated than rolling just one. The sample space helps us see that. And where is that useful? Oh, pretty much everybody that's spent any time playing games here, and a lot of different kinds of games, guys, knows the significance of some of these facts right here. Monopoly is my favorite right here, and the probability of dice rolling happens all over the place in Monopoly. Like, for example, there's a reason why when you start right here at Go, the square that's 7 units away is this chance one right over here, because that's the one that people tend to roll the most. And if you know stuff about dice and probability, you can use that to your advantage. Not to give too much away, but the one square on a Monopoly board that people land on more than anything else is the jail square here, because there's 3 different ways to end up on that square. You could roll there naturally, you could get a chance or a community chest that might send you to jail, or if you landed on this square right here, it sends you to jail as well. Now, from there, people are most likely to roll what numbers coming out of jail? Either a 6 or a 7 or an 8. Those are the most likely events. So if you were to think about where somebody was going to end up if they were on jail and rolled a 6, that would be St. James. 7 would get you community chest. You can't own that one. But an 8 would get you Tennessee. That's why when Mr. Fontana plays Monopoly, he always likes to own those oranges right there. In my humble opinion, those are the ones that people tend to land on the most. And yes, I've done spreadsheet simulations to verify that, but we don't need to get into all of that right now. All right, guys, so that's just kind of a quick crash course in what numerical probability looks like. There's also this thing that you saw last year in geometry called geometric probability. And it's really the same concept. We just use slightly different words to describe it. With geometric probability, we're usually talking about the concept of area. The desired area, what you're trying to hit, divided by the total area that you could hit. So let's see that in action right here, guys. Find the probability that a point chosen at random inside the rectangle will also fall inside this triangle. I meant to shade that and I forgot right there. Okay, so we want to know here, guys, if you're going to hit this big target right here, this rectangle, how likely are you to hit the blue shaded triangle? So just think to yourself right now, give me a percent, everybody. What percent of the rectangle do you think that triangle actually makes up? Maybe jot down your idea. Now let's find out if you're right. Here's what we need to do in a problem like this. We need to find the total area here, guys, which would be the area of the rectangle. And hopefully you guys remember from geometry, area of a rectangle is about the easiest thing in the world, base times height. That would be 11 times 6, which is going to be 66, and that would be square centimeters for the area of the rectangle. Then we would want to know the area of the shaded triangle. Now that formula is 1/2 times its base times its height, and the base of that triangle is the same as the base of the rectangle, which is 11. The height of that triangle goes from the peak perpendicular down here to the bottom, and that's going to be the same 6 centimeters here, guys, that we had for the height of the rectangle. So 1/2 times 11 times 6, that is going to be 33 square centimeters. So the probability here, guys, let's go back to our formula, is desired area divided by total area. The desired area is what's shaded. That's the triangle here. So it's going to be 33 square centimeters for your desired area divided by the total area that we could hit, which is the rectangle, 66 square centimeters. And what happens when we divide 33 by 66? Hopefully you see it, guys. That just simplifies to a 1/2. The units are identical on the top and the bottom. They just cancel each other out. Probability, even geometric probability, has no units, and the answer there is 1/2. So when I asked you guys to guess how much of the rectangle was shaded by the triangle, if you guessed 50%, that's exactly the right answer. And if you guessed something close to 50%, okay, you pretty much understood the concept right there. Hopefully now you see why the answer is exactly 50. And of course the joke is, I could have given you absolutely any numbers in the world here instead of 11 and 6, and this would have worked out exactly the same way. One last problem here, guys. This one's a little bit more complicated, but it's the same basic concept. Find the probability that a point chosen at random inside the square will fall outside of its inscribed circle. And it's not really a coincidence here, guys, or it wasn't an accident. I didn't give you any dimensions in this problem. And that's because the answer to this problem isn't going to change whether I shrink the diagram down to look like this or... Whoa, that was big. Or if I make it really, really big compared to the, oh my gosh. Let's try to put that back to where it was right there. That was kind of ugly. All right, it doesn't really matter, guys. We should be able to figure this one out regardless. Now, this is actually kind of a hint here for you guys. And for those of you who are going to be taking the SAT or the PSAT coming up soon, this might be a test-taking strategy you guys try to remember. If they didn't give you values that you thought needed to be there, that really tells you they don't need to be there. But what it also tells you is you could really pick just about any number in the world that you wanted. Like, for example, I'm going to say, how long do you guys want one side of that square to be? And I'm going to put a 10 right there. Let's say 10 inches. Now, this, what we're about to do next, is not a choice. If one side of that square is 10 inches, how long is this piece right here? Well, that's a radius of the circle, but it's also half of this piece cutting across the square. This piece over here would be 5 inches long. So let's write a few things down now, guys. The area of the square, base times height, would be 10 times 10. That would be 100 square inches. The area of the circle, hoping you guys remember this, is pi multiplied by your radius, 5, squared. So the 5 squared is 25, and then we would just stick a pi on the end of that. 25 pi, and that would be square inches for the area of the white circle. However, what we want is the shaded area. We want the area that's outside of the circle but inside of the square. So the way we come up then with the shaded area is by subtracting these two results. 100, which is the larger outer area, minus the inner one, which is 25 pi. Now I could put that in my calculator, but I'm not going to bother right now. I'm just going to leave it as 100 minus 25 pi. And now that you've found all your areas, the probability then, guys, is the desired area or the shaded area divided by the total. So the shaded area is 100 minus a 25 pi. And the total area for this entire figure is that 100 that we had right there. So let's very carefully, guys, go to our calculators and let's do this right. I would definitely do a stacked fraction. Okay, so for you guys, alpha and then the x key right there. And then I would type in the 100 minus the 25. Where's my pi button? There you go. 100 minus 25 pi all over 100. Now, before I hit enter, the question I would ask you guys is, if you took a look at this original diagram right over here, what percentage of the square would you guess is shaded? More or less than half. I think that one's going to be half. More or less than a quarter. Now, it might be getting close to that. So I would think it'd maybe be in that neighborhood of about a quarter or about 25%. So let's see what this one says, guys. I'm going to hit enter here, and we get it as a decimal, 0.2146. Now, again, you could leave your answer as a decimal. Doesn't work very well as a fraction. You could also convert that to a percent. So any way you want to do it, guys, would be fine. But I'll write it both as a decimal, 0.2146, but also as a percentage, where we just slide that decimal 2 to the right and get 21.46%. So either one of those answers is fine. You don't need to provide both of them, but as long as you've got it accurate to whatever the directions say in terms of rounding, that's going to be fine there. So about 21% of that square is shaded in. All right, guys, that's everything I have for you here from section 11.2 on probability. So dive into that homework and let's see how you do.